Good afternoon. My name is Henrique, and this work was also developed by my advisor, Dr. Helen Durand. I'll be presenting this work overview entitled Relating State Estimation and Computing to Control System Cybersecurity that summarizes our recent work in cybersecurity of chemical processes. In terms of the outline, we begin by introducing a background in process control and cyber-physical systems, and with special attention to cyber attacks in chemical processes. We also provide a background on a type of controller that can drive the process state to the operating steady state, as traditionally used by the industry, called economic model predictive control, or ENPC. We will introduce its control structure and its extension to Lyapunov-based ENPC. And using this control design, we present several techniques for detecting and handling cyber attacks. So to start, a cyber physical system and framework integrates control designs and physical processes and computer and communication networks. Although it advances process operation and enhances the capability to control the process, it also makes these connected systems more vulnerable to cyber attacks, which can cause change to the cyber physical components, such as sensor measurements, signal actuators, or controller and code, to directly affect the system dynamics. And because of this, cybersecurity is needed for maintaining the expected operation of critical industrial components. And cyber attacks can seek to impact on various concerns such as profit and safety, which may include, for example, alteration of data and product design, generally motivated by financial gain. And however, engineering strategies can be exploited, such as detection mechanisms and resilient controllers for cyber physical systems, which will be the focus of this talk. Although significant progress has been reported in the literature, additional strategies are needed to enable nonlinear systems under advanced control laws to be made cyber attack resilient. And control theoretical advances is a step toward resilient control designs, since it may add in attack detection methods. In this work, we consider a type of controller called economic model and predictive control with Lyapunov-based stability constraints, or an LNPC, and it has strong theoretical properties even in the presence of sensor noise and plant model mismatch. And particularly, we explore two concepts for utilizing this control design to attempt to detect attacks. First, we develop an LNPC with random control law modifications to probe for cyber attacks. And finally, we developed an output feedback LNPC with an attack detection strategy based on redundant and state estimators. And we now provide some preliminaries for the presentation by starting with the class of systems that we are looking at. So we consider that state, input, and disturbance are all bounded. We also consider that the process is stabilizable, meaning there exists some control law, in which we denote it here as h of x, and that is able to drive the process state to the origin. And the way that we will evaluate this mathematically is via Lyapunov functions. A Lyapunov function can be thought of as being like the energy of the system, because it takes a zero value at a steady state and takes large values as you move away from this equilibrium point. So this general terminology can be described by this figure here. We have this open set D, and where the time derivative of the Lyapunov function is negative, and you also have this another region, omega rho. This is called the stability region, which is a set of initial conditions where if you start the process state within that region, under the controller h of x, the process state remains in omega rho. And in fact, it will be driven to the origin, which is reflected by this blue trajectory here. We also assume that there are m sets of measurements continuously available, and the deterministic observer exists for each of the m sets of measurements. In addition, we assume that there exists a finite time TBI such that the difference between the state estimate Zi and the actual state X is bounded by a maximum value. For cyber-physical systems, cyberattacks can be understood in a dynamic system context. So consider this feedback control loop in which the controller uses the error between the process output measured by the sensor and the set point to compute the control actions to be taken by the actuator. And this feedback control loop may be used to regulate the process against disturbance or to track a set point that reflects certain process goals. A cyber attack, for example, may falsify state measurements provided to the controller. In this case, there is no more feedback response since the state measurement is false. So as an attempt to overcome this problem, state estimation may help with reconstructing and falsified states and detecting attacks. And this will be demonstrated in one of the our proposed techniques later. Since full state measurement may not be available, we define this general formulation of an output feedback ENPC. The main characteristics of an output feedback ENPC are an internal model that allows the prediction of future behavior, the criterion for optimization, and we have a general objective function that does not require to take any specific form, and the concept of a receding or moving horizon. That is, the optimization problem is solved every delta time units, where delta here refers to the sampling period, and its sampling time tk. We also have input and state constraints, and state estimates are based on the available measurements. And however, that general terminology does not guarantee or does not address issues such as whether or not exist control actions that cause all the constraints to be met. And also, it does not guarantee that you have closed loop stability. So that as a result, there are many variations on this control formulation to try to answer these questions. And the one that we'll be using in this work is the Lyapunov-based ENPC, or LNPC. This is a two-mode control design, where the first mode is associated with allowing the process state to vary over time and within the stability region. The second mode of operation is that shown here, where we have this blue contractive constraint. And what this constraint does is that it forces the process state to a neighborhood of the origin or steady state. Now we consider several detection methods which utilize the stability properties of LNPC to guarantee that several attacks can be detected under certain conditions. We provide two detection control concepts. The first detection method assumes full state measurement, that is Z1 equals the accurate state at tk. So for this first detection concept, we consider that NAV Lyapunov functions and Lyapunov-based controllers exist. Specifically, in the absence of an attack, if this contractive constraint is activated, the time derivative of the Lyapunov function along the closed loop state trajectory under the control of h of x is expected to be negative. This expected outcome suggests that attacks could be detected by seeing whether or not the Lyapunov function vi decrease over a sampling period. So to implement this control strategy, LNPC primarily operates the process in the baseline stability region on omega rho 1. So in this case, the LNPC is designed using V1 and H1. To prove for cyber attacks, the LNPC formulation changes at random proving times to one which uses Vi, Hi, and omega rho I, which is a subset of the baseline stability region. If no attack occurs, the mean Lyapunov function Vi should decrease over a sampling period. Otherwise, we flag as a potential attack event. We highlight here that this control detection concept does not guarantee to locate on cyber attacks, since Vi may also decrease even in the presence of an attack. What you can guarantee, though, is that if the Lyapunov function does not decrease, an abnormal behavior is detected. And here we have a chemical process example that illustrates detection strategy 1. We have a continuous stirred tank reactor with a second order reaction given by this system of equations. The control objective is to optimize process economics while maintaining the closed state in the baseline stability region. And this is the economic and cost function. The manipulated input constraints are related to the inlet concentration C0 in the heat rate Q. And the process model is in the input and affine form. These are the set of parameters for the LNPC design, and we used syntax formula to design the Lyapunov-based controller on H of X. The process was initialized on off steady state, and T0 was selected to be the proving time. So at T0, a new steady state XD is selected to design the subset of the baseline stability region omega 2. And these are the set of parameters to design the second LNPC. So in the absence of an attack, the closed-loop state can be driven to a neighborhood of this new steady state, which is reflected by this red trajectory here. And in fact, V2 decreases over a sampling period and following the switching time. Now we can describe a cyber-attack event which provides false state measurements on X1 and X2 at T0. Detection mechanism is again activated at T0. And what you can see here is that the V2 does not decrease over the next sampling period. In fact, it remains constant over time. And this is indicative of an abnormal behavior. In this case, we are able to unflag a cyber attack event. The first detection concept begs the question how we can guarantee that the closed state is maintained in a bounded region of operation and for all time. Potential way to tackle this question is to develop multiple redundant state estimators as part of the detection strategy. So particularly, if the difference between the state estimate Zi and the actual state X is bounded by a maximum value, this also implies that the difference between two state estimates, Zi and Zj, is bounded by a maximum value in X when no attack occurs. So if an attack is detected, that is, if the difference between Zi and Zj is greater than an Emax, we enter an emergency shutdown mode. An advantage of this detection concept too is that even in the presence of an attack, if the difference between Zi and Zj is less than Emax, we can guarantee that the closed state is maintained in the baseline stability region omega rho 2 over the subsequent sampling period. We have the same chemical process example to illustrate detection and concept 2. The only difference here is that we have only one manipulated input, which is the inlet concentration and Ca0. This is a set of parameters to design the LNPC, and we used, in this case, a proportional controller to design the Lyapunov-based controller on H of X. In addition, a high-gain observer is used as the redundant state estimator to estimate Ca from continuously available temperature measurements. The process was initialized on off steady state, and an attack was implemented after 0.3 hours of operation to attempt to drive the closed loop state out of the stability region. So the blue line here represents the attack policy, and the green line represents the state estimates trajectory. And you can see here that as soon as the cyber attack was implemented, we were able to actually unflag the attack event as soon as it was developed. After 3 hours of operation, the difference between the attack and event and the state estimate was above the threshold that we designed. So in terms of conclusion, we developed detection and attack mechanisms using LNPC that takes advantage of control and theoretical guarantees in detecting attacks. We first developed a randomized LNPC change to probe for cyber attacks. We randomly modified the control law in such a way that we should create a specific outcome if no attack is occurring, by evaluating whether or not the attack malfunction is decreasing over time. And however, there's no guarantee that these detection methods can actually detect an attack. Finally, we developed a cyber attack resilient output feedback LMPC based on state estimation and detection and control framework. In this case, we assume that multiple state estimators are available for the process. And with that, we'd like to thank the Air Force and Office of Scientific Research, National Science Foundation, and Wayne State University for the financial support. And thank you very much for your attention.